All right, I want to talk about Lab 1. We were studying acceleration being directly proportional to force. So acceleration is directly proportional to force. This is only true if we hold the mass constant. Constant. Now don't forget, this equation pertains to the system, right? The whole system we're talking about, which is the car plus the hanging mass. So it's both of those. Both the hanging mass and the car are part of the system. So you've collected data to measure acceleration and F. What is F? Well, F is actually the sum of the forces acting on the system, the net force, you would say, right? So just keep in mind what that is. And all we care about are external forces. So the Fg1, and this right here is Fg2, Fg on mass 2, and this is Fn. And we're ignoring friction. So if we were to write the sum of the forces, we would say Fg1 plus Fn plus Fg2. But these forces right here cancel each other out. So the only force that we need to be concerned about is Fg2. So you've recorded the mass, we'll call that M2, of whatever was hanging from lab 1, and you just multiply that by G, and that gives you Fg2, and that will give you Fnet. So you should have a table of acceleration values that come as a result of modifying Fg2, which is Fnet. Right, so you're going to use this table to make a graph. All right, acceleration measured in meters per second squared as a result of Fnet changing, measured in newtons, right? And you're going to use Fg2 to get Fnet. And you should see that the points, approximately make a pattern, and you're going to estimate, you're going to do a best fit line, and calculate the slope of that line. The question is, what is the meaning of that slope? Well, to figure that out, we've got to use Newton's second law, ma. So we can start with this, or we can rearrange this equation, right? This is the same thing as A equals the sum of the forces divided by m, just dividing each side of the equation by m. And why would I want to rearrange it? Well, because A is graphed on the y-axis and Fnet is graphed on the x-axis. Whoops. Right? So now I can see that A is y. And I'm going to do one more thing over here. Let's back up. Let's slow down. Let's say A equals sigma f times 1 over m. Okay? So all I did is I broke this division into multiplication by multiplying by 1 over m. Same thing. Now, A is my y variable, and this is my x variable. Okay, x times 1 over m. What I kind of want this to look like y equals mx plus b, or I'm going to say ax plus b, right? Where a is the slope. Maybe you're used to mx plus b. It doesn't matter what that variable is. That's not acceleration. That's a dummy variable. I'm not using m because then it would look like mass. So whatever this coefficient of x is the slope. And we want to know what that is. So I'm gonna transpose these because in multiplication you can do that. So I'll say 1 over m times x. And now, right, I have y equals 1 over m times x. Now be careful, m is the mass of the system. Well, whatever comes in front of x is the slope. All right, whatever comes in front of x is the slope. I don't even have a b value, so I could write plus 0 in order to get it to match this format over here. But the question was, what is the significance of the slope? Well, according to this equation right here, my slope is 1 over m. So let's say I did a graph. Let's say I did a graph and I calculated my slope, and my slope was 4. It would be, well, if I do the units for slope, well, I won't get into that right now. Let's just focus on the numbers. 1 over m. Well, how would you use that to solve for m? And why would you solve for m? Well, it's telling me my slope is equal to 1 over the mass of the system, right? M is the mass of the system because the equation was modeling an entire system. I can solve for m. The easy way to do it is a little math trick is just say m system equals 1 over 4. But that's a little math trick where you invert both sides of the equation. If you really want to show your steps, right? If you really want to show your math, you multiply each side by m system, right? Whatever you do to one side, do to the other, and then you would divide each side by 4. Notice just drawing this line right here allows me to divide by 4. And then that equals 1. 4 divided by 4 equals 1, and I'm left with m system equals 1 over 4. And I just figured out the mass of the system, 0.25, and it's going to be kilograms, right? If you show your units. I didn't show any units anywhere, but if you want to know where the units come from, right? The slope is rise over run. That's the rise over the run. And my rise units are meters per second squared, and my run units are newtons, which is kilograms meters per second squared. So I'll show my slope units over here. So slope is rise over run. In this case, meters per second squared over, this is the rise, by the way, this is the run, over newtons, which is kilograms meters per second squared. That's the definition of a newton. And if you clean this up, this cancels, and you're left with 1 over kg. So if I were to go back and put units into the slope, when I said the slope was 4, I should have said 4 times 1 over kg times 1 over kilogram. And then to get rid of that, I'd multiply each side by kg. And then it would disappear here and show up on that side, and that's why it shows up there. So that's a lot. It's kind of convoluted, but that's the explanation for units. Now, in the lab 2, we were saying, okay, let's hold the hanging mass constant. So in lab 2, the hanging mass is constant, which means F net is constant. So F net equals mass of the system times acceleration of the system. And this was constant. So these are two variables, A, acceleration of the system, versus mass of the system. We kept adding mass to the car. And what we should have seen was a graph where the points make the acceleration decrease, right, as the mass increases. Okay, this is not linear, but if we graph 1 over m, those points should be pretty linear. And again, we can get a best fit line through our points and find the slope. And again, the question is, what is the slope? Well, notice once again, we've got a on the y-axis, and 1 over m is our x variable that we've plotted. So I'm going to rearrange this equation, knowing that I need this to be by itself. So I'm going to divide by m. So I'll divide by m, mass of the system, and you get A equals net force divided by m. Okay, And I'm going to parse this out because we didn't graph m, we graphed 1 over m. So I need 1 over m in my expression. So I get A equals net force times 1 over m. Well, this is perfect because at this point we have acceleration and 1 over m, and they both show up in our equation. So that's great. Why is that great? Because A is our y variable, and 1 over m is what we plotted on the x-axis. So what is this thing? That's our slope. So the question was, what is the slope of this line right here when you plot A versus 1 over m? And the answer is the net force, right? So if you find the slope on that graph, you should find that the slope is exactly equal to what you got from the hanging mass. So here's your car, and this force right here is Fg2, which is the only force causing acceleration. So whatever that value is, m2 multiplied by g, that value should match the slope of this graph.